Alright, so we are still on the modeling of system, right? And we've seen that, and if we are modeling the system, basically means that we are using math to describe the system, right? We are using math to describe a system. So it could be something like AB is equal to C. Basically, it's a mathematical model or an equation, right? Describing a system, right? Alright. But then before all in the model of the system, there are a whole lot of things that must be understood, right? So we have something that we call state variables, right? And what they do is that they describe the current state of the system, right? Current state of the system. So state variables, right? So this is what we call state variables. And these are variables that describe the current state of a system. So in the what do you call it? The the tank react what do you call it? The continuously stirred reactor system that we have. For that one, for instance, the one that describes the state of the system will be something like some of them will be state variables will be something like temperature, right? And then we could have height, right? And we have concentration, depending on the system, right? So these are the variables, right, that are needed to fully describe the current state of the system, right? All right. And then there's also another concept that we should talk about, right? Which we call dead time. Okay, dead, yeah, dead time. Let's try this one. So what that one says is that there are some systems like that. There are some systems where there's a delay between the input and the output. All right, so let's say we have a pipe, for instance, something like this, right? A pipe, right? And then fluid is moving through it like this. So let's say fluid is moving through it, and then the temperature here, after when we measure the temperature here, right? The temperature is here, let's say, is about 20 degrees Celsius. But at that same point in time, if you measure the output temperature, so this is the input, right? So at that same point in time, if you measure the output temperature here, output temperature at the same time, it's not the same as the 20. So it's about, let's say, 10 degrees Celsius. So meaning that there's a delay. So that's what we call the dead time. So for something like that, for instance, if you are modeling the system, you must consider all these things, right? You must consider all these things. So what that says is that there's a relationship between the output temperature and the input temperature. The input temperature. So it can be something like this, where we have the T out as a function of time is equal to the T in, but are delayed by what we call is delayed by what? We don't know the time, right? So something like this, where this is the time, right? And this the and we write the dead time like this, right? So whenever you're modeling a system that where there's a delay like that, you must consider that as well. So you must consider the dead time, and you must find the dead time. And then we are seeing that for this dead time, it is described like this. We have the length of the pipe. So if you're using this instance, it is the length of the pipe, right? All over the velocity of the fluid in the pipe, right? So that's velocity of fluid. And then when you do the dimensional analysis, you get to see that actually it gives you time in terms of s, right? Because length is just, so let's say if it's meters, right? And here velocity will be meters per second. And when you do the everything right, you end up getting s, right? So that will give you the delay time for a particular system, right? Yeah. And then one other thing that we must talk about is that whenever we are describing the systems, there are fundamental quantities that we consider, right? And then these fundamental quantities are, if you've gone through some momentum, isn't it? Transport phenomena, you get to know that they are mass, right? Energy, and then momentum, right? So most of the times, especially with the theoretical approach of modeling a system, right? These are the three main conservation equations that are used, momentum, that are used when modeling a system, and then we kind of do some assumptions, remove some out to get the equation that describes the system, right? Yeah. And then another thing too is that whenever we are designing a system, right? It's not always that you have one input, one output. So if you use this one, for instance, let's see the continuous tank reaction that we have, for instance, let's see. Mm, because these are other things that you must consider as well, right? So basically, what we are doing right now, we are to talk about some of the concepts that must be considered when you are trying to model a system, right? So if you look at this one, for instance, you get to see that the input is not just one, right? So we have one input, another input here, right, and the output, and another output, right? So that will mean that there are systems where the input is one, the output is multiple, right? So let's try them out. So we could have single input, single output, and you could have single input, multiple output, and you could have multiple input, single output, and you could have multiple output, multiple input, multiple output as well, right? So each and every system of this, as we said, will have its own way, or you have a whole equation that describes it, right? Each and every one of them will have its own configuration and how the equation will describe it, right? Yeah. But one important thing is that whenever we're having the systems like this, one thing still remains relevant, what we call the transfer function, right? What the transfer function is that because we have in a system like this, and our aim, as we said, is to produce a particular product, or do you have a particular output? What the transfer function does is that, right, it compares the output to the input and see what happens to the output when there's a change in the input, right? So this transfer function, the general form is something like this. We write them as G, S, right? And then we say that is the ratio of the output variables, right? Variable could be plural, right? Whether it's a multiple input or multiple output or something, right? And then we compare it to the input variables, right? So it's just saying what happens. The transfer function just tells you what happens to the output function when the output variables, when the input variables experience a change, right? So that's what they are doing, right? And then again, this one too could be multiple, right? As we've said, right? So that's what the transfer function does, right? And these transfer functions, they can be built from the ordinary differential equations themselves, right? Or at times, or in cases where the process is not described by just one equation, but described by multiple equations, or where you have multiple transfer functions, you can they can be solved using the matrix form, right? So let's say we have a uh, system that has two equations described in it, and both of them has been transformed into, let's say, the Laplace transform has been done on both of them, right? So let's see something like this, this, right? Let's see, and we have this one, two s, we have this, two s, right? We have another one like this. It's kind of like equation two, right? Where we have this one, two s. Then again, these are some of the concepts that must be understood when modeling a system, right? This is one. Okay, this is still two, right? Okay. So what this means is that because, so as we said, right, so you can see that the transfer function, we know the general form of the transfer function, the symbol is G, and so you can see different G's here, about four, right? So what this means is that in this particular system you need like kind of like four transfer functions. So what it says is that for you to be able to know the number of transfer functions that you need, right, you kind of like multiply the number of input variables by the number of output variables, right? So in this case, for instance, we have let's see. So we clearly know that the input variables are these, right? So let's see. Here we have so this is actually one. This is F1, and this is F2. This is F2. This is F1, right? So looking at this one clearly, we know that the input variables are these, right? F1. Let's see. Are these F1 and F2, and then F1 appears here again, F1 appears again. So basically, so simply what means is that we have the input variables, right? So let's compare to this one. The input variables are two, right? And the output variables are two as well, which is y1 and y2. So when you multiply this by this, it gives you 4. So that's why we have 4 transfer functions describing the system, right? 4 transfer functions describing the system. So we actually use this one when there are multiple equations describing the system, not just one, right? So that's a normal case when we get this one, right? Another thing too is that when, and we should take note that this could be the case. Let's clean this up. The two equations we are seeing here could be the case where in a system where we have multiple input and multiple output, specifically two, what's the name? Two outputs, right? And then what? Two inputs, right? So let's look at this very well. We've seen clearly that we have F1 here, and then we have there should be an F1 and F1 here too, right? So F1 and F1, this is one input, F2 and F2, one input, another input, right? And outputs are two. So clearly this is a multiple input, multiple output system, right? And then even for these ones, there are ways that we can go about in solving, like in kind of like solving these equations and finding the output, right? Yeah. Or finding the transfer function within them, right? Yeah. And then we also got to see that we've gotten to see that for in this system where we've seen the transfer functions, right? So we've seen that the transfer functions are generally of this form, right? Where we have let's write it this way. So it's a ratio of the output variables, right? Variables, right? And then the input variables, right? Input variables, right? Right. Yeah. So if you don't see that and you see this, you see there's the output, right? As we've seen in the equations above. And then if you see this as well too, that's the input, right? Yeah. So this is still the transfer function. If you don't see that and you see this as well too, it's still the same thing. This is the output, and this here is the input, right? And whenever we have described the system and we have the transfer functions, right? Generally, what happens is that the root of the what you call the numerator and that of the denominator gives us certain information about the process, right? As we said, we are modeling the system, and when we model the system, we get the transfer function. The nature of the root of the numerator and the denominator gives us certain information about the system, right? So let's see. So let's say we have a system, and then even the root of the numerator and root of the denominator, they tell us different things about the system, right? So let's see. So we are trying to get a sample, right? So let's see. Okay, and then we know that when it comes to these things, when it comes to root, they are generally kind of like 3 forms of root that we can get from a system, right? They're generally 3 forms. So the roots of the numerator are what we call the zeros of the transfer function, right? And then the roots of the denominator, which is the p, are what we call the poles of the transfer function, right? And the nature of this root tell us can give us a lot of information about the whole thing, about the process itself, right? So let's see. So let's say after modeling a system, we have something like this or this, or right? Where we after we made what do you call it? The objective function, the subject, we have something like this. So this down here is what we will call the characteristic polynomial, right? And this is a general form. It could be of any form. When you expand, you get a polynomial. So let's say we have a polynomial of this form. Let's say we have something like this, right? Which is basically right. The highest power is 2, right? Depending on the root can give us a whole lot of information, right? So let's say if it happens that the root so here we expect 2 roots, right? So if it happens that the roots are both, so let's say the roots are less than 0, then we can say the system is stable. And as such, something like this can be said about it, right? That let's say if this is the quantity x of interest and this is time, right? The system stability will be something like this. So if the system is stable and there's a disturbance, there's a disturbance like this, the system on its own can kind of settle back to the steady state, right? So we can say the system is stable. But if the root happen to be equal to 0, right, then we can see that uh and we can see that what's the name? The system is oscillating with a constant. The moment there's a disturbance, so let's say something like this, and the moment there's a disturbance, right, the system will keep on going like this, right? So meaning that the system will have a constant oscillation with a constant amplitude. Right, that's it for, so basically you're still describing the systems, right? The stability and then the shape of what do you call it, the system, right? And if it happens that the root of the or the poles, right, in this case we are talking about the denominator, right? The poles, right, happen to be greater than 0, then we can see that the system is unstable, right? Because it will be something like this. That will mean that if you are describing, let's say, the stability of the system, if let's say it's stable, but then there's a disturbance, right? What happens is that it either goes this way, which means unstable, or it comes this way, which is unstable, or it goes this way, oscillate gradually, increasing amplitude of the oscillation, right? Which is also unstable, right? So these poles and then the zeros tell us a lot about the stability, right? So this is stable, and then they even go on to even tell which configuration system to use for a particular system, right? And this here is unstable, right? Give a lot of information about the system, right? And then so clearly the poles here give the system stability, right? And then stability, right? And some other information, but here you're looking at just this field. And then the zeros can tell us the shape of the response, right? The shape of response of the output, right? Yeah. So these are some of the information that these two can give us, right? Okay. And then also we said modeling the equation, right? Another thing that we must consider is that when we are modeling an equation, so we know that math, talk about math, definitely within an equation. So let's say plus b equal to c. So definitely this is an equation, right? And within the equations we have what variables, right? Yeah. So there's something that we call degree of freedom, right? Degree of freedom, and it tells whether we've been able to sufficiently describe a system, or we are describing it too much, or too much constraints, right? So degree of freedom, right? So this degree of freedom that we talk about is usually represented this way, and we say is equal to the number of variables minus the number of independent. So the thing here is the number of variables or independent variables minus the number of independent equations. So these variables and these independent equation. So I think it's you are that. Yeah, yeah, independent equation, right? So if it happens that we have a particular system that this degree of freedom, right, is greater than 0. So let's see, there are three values that the degree of freedom can take, right? This f that we're talking about, degree of freedom, right? There are three values. It's either the f is equal to 0, right? After we do this computation here, right? Or the f, let's see, or the f, degree which is the degree of freedom, right, is less than 0. Or we could have the degree of freedom being greater than 0. And each of these ones tell a particular thing about the modeling that we are doing. So if you model the system to such a point that the number of variables, the number of variables is the same as the number of independent equations, then we can say that we have fully specified the system. So this is what we call a fully specified system. Specified, right? We fully describe the system. That's what it's saying. So basically, the degree of freedom is just saying that what is it? The number of variables, right? The number of variables that are needed, right, to completely describe a system, right? Completely describe a system. So there's at times the system can be overspecified or can be underspecified, right? Yeah. So let's see. So if we have the variables being equal to the number of equations, then we see that the system is what? Fully specified or exactly specified. To mean that you can actually get the result that we are looking for, the solution to the system easily, right? But there happens a case where we have so if it is this way, where we have the degree of freedom to be less than 0, then that will mean that the system is overspecified, right? And then we'll talk about that. So this will be over specified, right? And what that means is that if it's greater than 0, so if it's less than 0, what that means is that the number of equations are way more than the number of variables, right? So you end up getting the degree of freedom to be less than 0. So mean that you have a lot of constraints. You can solve it. What's the name? You can you cannot get a solution because there are a lot of constraints, because the equations are way more than the variables describing the system, right? So it's over constrained, right, or over specified. And if you have a system where the variables, right, sorry, the degree of freedom is greater than 0, meaning that the system is so under specified, right? So meaning that you basically just have to make sure that the number of equations match the number of variables, right? So this will be under specified. That means I either have to remove some of the variables, right, or add some of the equations, right? And there are a lot of ways of correcting these things. When you have a system to have to be over specified or under specified. So let's talk about some of them, right? So let's say that's things to ensure that, or how to ensure that the degree of freedom is 0, right? How to ensure that this degree of freedom is 0, right? And there are a whole lot of ways of doing it. So let's talk about them. We are not going to write. So let's see. We know clearly that if it happens that the degree of freedom, which is the f, is less than 0. If it's less than 0, that means that it's over specified, right? Over specified means that there are a whole lot of equations, right? If there are a whole lot of equations, then meaning you must remove some of the equations, right? Or remove some of the constraints, right? But then if it happens that the degree of freedom is greater than 0, that will mean that you have to add more equations, because in that case the equations are less, right, than the variables, right? So these are some of the things, but practically what that will mean that is either you have to introduce more loops, right, in the system, especially uh, when you have a cascade system, for instance. The moment you introduce a loop, meaning that you introduce an equation, right? And then it could also mean that you also kind of like introduce external disturbances, which is also another way, right? External disturbance. Right? There are a whole lot of ways of doing this, but all in all, it's just to ensure that the whole thing is to ensure that the variables, the number of variables are equal to the number of independent equations. Because when these two are equal, then we end up getting f degree of freedom to be 0. Then we can see the system is all fully specified, right? Yeah, fully specified.